Hello everyone, good morning, good afternoon, good evening. Today we learn one important concept in conversion of alkyne to alkene. To be specific, we are converting alkyne to trans-alkene. So the important reagent we are using here for this conversion is sodium in liquid ammonia. This is a wonderful reaction and very nice. Okay, so wonderful mechanism it has. One more reagent we can use before this. Okay, artificial effect coming on its own. So if you simply take an alkyne, say the simplest alkyne is ethine, and if you take a palladium catalyst, palladium charcoal, and do the hydrogenation. So if you take 1:2, 2 moles of this, what you are expecting, it will not stop at alkene stage. Both the pi bonds will reduce and you will get a CH3. CH3 means C2H6, ethane you will get. That was the problem. They thought that if we change the ratio 1:1 mole, if you take, you will get a double bond here. That's what they thought, but actually that did not happen. They got the mixture of this as well as this. Then they thought, then how we can stop the reduction or conversion of using an alkyne? How do you get the alkene? So that they have already solved many reactions of alkene, so we can use all of that reactions for alkynes as well if you convert it into alkene. Okay, so then first thing they tried poisoning the catalyst. What they did, they took the catalyst palladium on carbon, and to this they added a little bit amount of lead carbonate and quinoline, an aromatic compound, quinoline. Then they observed that if you take, say like this, substituted alkyne, you are getting an alkene only the cis form of alkene. If these are two different groups, you will get the Z form, right? Cis or Z alkene you are getting. Wonderful. Then they thought, and what do you call this reagent as? This catalyst as Lindlar's catalyst. Lindlar's catalyst, right? So if you use a Lindlar's catalyst, you can convert alkyne to cis-alkene. Alkyne to cis-alkene. Remember, very important catalyst. Now they wanted to get the trans-alkenes from the alkyne. There where our today's concept comes. Today's concept 0 is sodium in liquid ammonia. So the simple reaction I will write first. If you take the same CH3, so here sodium in liquid ammonia, what you will get? Trans isomer. CH3, trans means these two are opposite, hydrogen are in opposite, so this is a trans-alkene you are getting. From where? From alkyne. See, now the question comes, why in Lindlar's catalyst it is coming cis-alkene? Why you use sodium in liquid ammonia it is coming the trans-alkene? Okay, Lindlar's catalyst reaction mechanism we'll see later, but I'll just tell you that in case of Lindlar's catalyst, when you use, what happens is there is a syn addition of hydrogen. Syn means from same phase. This is alkyne, it is a linear molecule like this, so hydrogen will come from here or it can come from here. Only one phase, syn addition. So syn addition will give you cis isomers. There is no stereo specificity there. But when you come to this sodium in liquid ammonia, here we are expecting anti-addition of hydrogen. One hydrogen is coming from the bottom, another hydrogen is coming from the top. Okay, that is called anti-addition. Second one, because it is the triple bond is converted into double bond, you can also call it as reduction. And because the hydrogen is added, you also call it as hydrogenation. Okay, and because it is anti-addition and giving you trans, you say that it is stereo specific reaction. So enough of the talks, let's go to the mechanism. We'll take this reaction only, then we'll write the mechanism for the same reaction. Very important. Try to understand. I will try to make it as simple as possible. Mechanism. Okay, what is the starting material here? CH3, C triple bond, C CH3 for butane, but2-ine. Okay, this is alkyne. Now what is the metal we are taking? Sodium. Whenever there is a sodium, remember, in any organic reaction, sodium or any metals, they usually give the electrons, and most of the time when they give one electron, usually for group 1 elements, they will give the radicals. So this fellow will give one of electron to carbon. Now you will ask, already carbon has 4 bonds, why it will take the electron, right? Do you remember that carbon-carbon double or triple bonds are unsaturated, therefore they are reactive. Carbon-carbon single bonds, they are saturated, they are non-reactive. They always want to become saturated, therefore this will give an electron and this carbon will take it. Once it takes it, what is left here? Minus Na plus. I will write here Na on top, Na plus is gone. Okay, what will form here? CH3 C, one dot, right? Meanwhile, what happens? One of the pi bond will break and both electrons of pi bond will come on the next carbon. So you will get a double bond C, 2 electrons will come on this. So therefore a negative charge, again CH3. Understood? Sodium will give 1 electron to this carbon, it will become a radical. Meanwhile, at the same time, the carbon, one of the 2 pi bonds, there is 1 sigma 2 pi bonds, one of the pi bonds will come, break, and both electrons will be given to this carbon, therefore it will have a negative charge. Okay, now the problem with this structure is, see, where these electrons will be in orbitals. So I will draw an orbital like this, another orbital like this. Obviously you know that already when there is electron density and both the orbitals are side by side, there is a more repulsion. The repulsion is more repulsion between the electron density. Therefore, usually for radical, cation and anion, what is the structure? Trigonal planar, this kind of structure. So it will also try to assume or acquire same structure so that it can reduce the repulsion between the radical and anion. So this intermediate, what do you call? A radical anion, because both are there, radical is also there, anion is also there. So now we can write this. How you can write this? Let's go to the next part. CH3 carbon, 1 dot I will write here, then double bond C. The both electrons with negative charge I will write here, and this carbon will come here. Now how it is trigonal planar? Because you have to draw a orbital here. Now you can see 1 2 3, 3 molecules on same plane. For this carbon, 1 2 3, 3 atoms, or here you can consider lone pair as the orbital, and all of them are in trigonal planar. So now why this will become stable? Now the reason is, now electron densities are in opposite direction, they can here like this, they can stay, they will become more stable compared to when electron density is like this, right? So therefore now what happens? Acid base reaction will take place. Okay, you think base means we have used ammonia, so this may be base. No, here liquid ammonia is acting as an acid. Yeah, you heard me right. So you take HNH2 like this. HNH2. Now this is carb anion. It needs hydrogen. It always search for hydrogen, not hydrogen, proton, H plus. And this hydrogen attached to nitrogen is active. Active means the hydrogens attached to electronegative atoms. So this will take this proton. Proton means this will just come as a without electrons. So both electrons will come and sit on this nitrogen. So what will go from here? Minus NH2 minus. These low pairs are already there. These extra electrons came now. Right? Minus NH2. What is came here? H plus. So now what you can write this? CH3. Be careful. See here. There is a radical as such. Double bond. Carbon. It took hydrogen from here. And this CH3 is as such. Right? So this is a orbital with still one electron. Okay. Now it is only a radical. Now what happens? Another sodium atom will come into picture. There are plenty of sodium atoms. You can bring one more sodium atom. Another sodium atom. Okay. That another sodium atom will give one of its electrons to this carbon again. And it will go as minus Na plus. Right. So this will become anion now. So the structure will remain same, CH3C with 2 electrons and negative charge, double bond C. Okay, here H, here CH3. Right? So now you will draw this orbital here. Now again what will happen? The same step will repeat. You bring one more NH2 here, NH3 here. I will write NH2 and H minus NH2 minus will go. Right? So again this carb anion will take one of the protons and it will become like this CH3 C, H came here, double bond C, H came here and here. Now if you see how the hydrogen is added, one came from top, another came from bottom. If you keep this on the surface of this board, one came from top, another came from the bottom. So this is called as anti-addition. Anti-addition. If both come from the same face, both from bottom, both from the top, then it is syn addition. Okay. So why it is anti? Because of this structure, stable structure of radical anion. Okay. So what you got here? Trans or E. If these are two different groups, then you call it as E isomer. So this is trans-alkene. Trans-alkene. Right? So this is a beautiful mechanism of sodium in liquid ammonia. Okay. So overall you have to see what happened here. You never add hydrogen here. Don't write a H2. We never added hydrogen here, but still you got hydrogen and hydrogen. How you got? We can write hydrogen like this. H2 we can write how? 2H plus 2 electrons. Right? Now, so where these electrons and H plus came from? Sodium. One sodium atom here, another sodium atom here. One sodium, another sodium. Both gave one electron, it's total 2 electrons. So these electrons came from 2 sodium atoms. So what is left? 2 Na plus. After losing electron, Na plus. Here Na plus, 2 Na plus. This H plus came from where? Ammonia. One ammonia here, another ammonia here. So 2 ammonias. Okay, I will write here 2 ammonia, liquid ammonia, liquid will give 2H plus and they will come back as what? 2 NH2 minus. So actually hydrogen came from the ammonia, hydrogen not, H plus came from ammonia, electrons came from sodium. So this is electron transfer mechanism, right? So what is left then? 2 Na plus and 2 NH2 means what is left? 2 Na NH2, sodamide, 2NaNH2. Got it? So this is the reaction mechanism of sodium in liquid ammonia, which converts alkyne to trans-alkene. Selective, stereospecific reaction, anti-addition. Okay, hope you understood this. Like this, we'll bring more reactions on organic chemistry, try to make you understand. Thank you so much for your time. We'll meet next class. Take care. Bye bye.